we are going to move to another topic which is really important, which is capacitors. Capacitors are really devices that they are used to store electric charge and energy, and they are real, very important electronic components. You're gonna find them in almost like everything, and we're gonna say that the amount of charge that we can actually store depends on two major factors. One of them is the voltage applied, and the other one is the capacitor's physical characteristics like size and area. And we are going to talk about these in a little bit. For example, when I have a parallel plate capacitor, it is just like two plates. One of them is positive, one of them is negative. They have equal charges, but they are opposite. And we can calculate the capacitance. This is a general formula for any capacitor, not only for parallel plate. We charge that we this is the capacitance equals the charge divided by voltage. It is measured in a unit called farads. Now, a Q, it is the charge and it's in coulombs, and V, it is the voltage and it is in volts. 1 farad equals 1 coulomb or over 1 volt. Now, for this specific parallel plate capacitor, the capacitance, it is a constant, the electric constant, which is 8.85 10 to the negative 12, multiplied by A, the area, divided by D, which is the distance between the two plates. That A, it is the area of one plate only, not both. And D is the distance between the two. Now, most of the time we are adding a material, we call it dielectric, between the plates of the capacitor, and these we add them so that we're gonna have more capacitance. Okay, adding insulating materials between the two plates is gonna have the capacitance going higher by this amount, which is really kappa. And of course, different materials, they have different insulating materials, they have different Ks. This is a different K from the one that we used with electricity. Now, I can connect capacitors in series or in parallel. In series, when you're gonna find them like this, okay, one after the other. And here, what we need to know that when they are connected in series, the charge here is gonna be the same for all. Then if this is, let's say, Q1, then it's gonna be Q1, 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 Q1. All of them, they're gonna be having the same Q. But their voltage is gonna be, the total voltage is gonna be the voltage on the first capacitor plus the voltage on the second plus the voltage on the third. And this is how we are going to calculate what is called the equivalent capacitance. Equivalent capacitance means I will replace all these three by one capacitor. I'm gonna call it C series, CS. On the other hand, there are occasions where I want to connect capacitors in parallel, and this is when they are like this. And here the voltage is gonna be constant, and all of them, they're gonna have the same voltage. Then if I have, let's say here, a 12 volts, every capacitor is gonna have a potential which is 12. Now the total charge is gonna be Q1 plus Q2 plus Q3. And if I want to calculate the capacitance in parallel, I'm gonna add all the capacitances. All right. Now, most of the time, I don't have just a single arrangement. You will find that they're gonna be mixed, and I'm gonna show you how we're gonna do that process. Now, as I said, we use capacitors to store charge and therefore to store energy. And then When we are going to calculate the energy stored, we're going to multiply Q divided by V over 2. Or if I will use again, look here at this formula, the one that I did use here, C equals Q over V, I can remove Q and put here C times V. Therefore, the formula, this is another form of it, and this is the third form of it. Then it's like just these are really equivalent forms depending on which material, which quantities are given. Here, this is a direct application of the first equation. Calculate the voltage applied to 2 micro, remember, 10 to minus 6 farad capacitor when it holds 3.10 micro coulomb of charge. And that one is, again, 10 to the negative coulomb. Q equals C times V, and therefore the voltage is Q divided by C, and it is 1.55 volts here. This is what I was talking to you about. Find the total capacitance of the combination of capacitors shown in here. I will say the good strategy is always try to label them. Here what I did, I said this one is C1, this one is C2, this one is C3, this is C4, C5, C6. We usually move backwards, okay? Then when I'm gonna first look at this arrangement here, look here, this is C1 and C2, they are connected in parallel. Therefore, I'm gonna say C12, the equivalent of C1 and C2. It is now the rule, it is this one, adding. Okay, therefore, I'm gonna add 15 plus 0.75, and that is gonna be 15.75. Now, my arrangement is gonna be, the new one is gonna be, that one is the 1.5 microfarad, and I can replace the 2 by just 1, which is the 15.75. Let me draw this for you. And here, I'm gonna have that second one, which is C4 here, and then the rest here is the same. Okay, now what's gonna happen is, now if you look at now this one here, I did call this one C12, and that one is C3. These are really in series, therefore I'm gonna apply the series law, which is this one. And here I'm gonna say C1, 2, 3, because I am collecting the equivalence of the equivalent capacitor of all the three. And then here I can say simply this one is this one. And then I will be able to calculate 1.5 microfarad times 15.75 divided by 1.5 plus 15.75. And then I ended up with having 1.37 microfarad. Now what I can do is the following. I can redraw this as, okay, this one here is gonna be the C1, 2, 3, and this is the C4. And the rest, of course, is gonna stay the same. Also, here, what I can do is, I can simplify 5 and 6 and calculate what is really their equivalent. Then I'm gonna add another one here. That one is gonna be C56. And then here I said C56 is 2.0959 microfarad. And then I ended with having all these three as they are really in parallel. and therefore I will add them. Then finally, after calculating C56, 2.056, 2.059, I can add all of them to be 11.429 microfarad. This one is on how we are going to calculate voltages or charges on capacitors, so that we can actually also calculate energy. Suppose that you have 9 volts battery and a 2 microfarad capacitor and a 7.4 microfarad capacitor. Find the charge and energy stored if the capacitors are connected to the battery in series. Do the same for parallel connection. Then I'm gonna do first, this is the series connection. Then I will say first I need to find what is the equivalent resistance, which is C1 over C12 equals 1 over C1 plus 1 over C2. And then C12, it is C1, C2 over C1 plus C2. And that is 1.575 microfarad. Now, this is the new circuit, and something that we need to know that I can calculate that here, what is called total charge. And since, remember, this is series, then this equals Q1 equals Q2. All right, and E here can be calculated as the value of the capacitor times V squared divided by 2. Remember, the E has units of joules. I can do this for parallel, and that is, they're gonna be something like this. This is C1, this is C2, and that is the voltage here, okay? And then I can say that their equivalent is gonna be C1 plus C2, which is 2 microfarad plus 7.4 microfarad, which is 9.40 microfarad. I can find the total charge, which is 8.46, which is the equivalent resistance, equivalent capacitance times the voltage. And then from that, I can calculate the amount of energy. And you can see here that the total amount of energy is more when we are connecting in parallel. Thank you and have a great day.